Hello and welcome back. We are on none other than lesson 11-4, extending the congruence criteria. So back in lesson 11.2, we learned that there are a couple shortcuts or congruence criteria that can prove two triangles congruent. And in lesson 11.3, we really dove into why those congruence criteria work. The side, the side, angle, and then the angle, side, angle. And we said some really powerful things about how, for example, on side, that if three sides of one triangle are congruent to corresponding sides in another triangle, then those two triangles are congruent. And then for side, angle, we said if two sides in the included angle of one triangle are congruent to corresponding sides in an angle in another triangle, those two triangles are congruent. And then we also looked at angle, side, angle, which says kind of the opposite now. If two angles in the included side of one triangle are congruent to corresponding angles in included side of another triangle, then the two triangles are congruent. But we learned back in lesson 11-2 that there's actually another congruence criteria, or shortcut if you will, known as the angle side criteria. So that's the one we're going to look at in this lesson. So before we go any further, let's take a look at our learning targets. So we will apply congruence criteria to figures on the coordinate plane. So see how that works, how we can prove things not just off the coordinate plane like in 11-3 using rigid motions, but we can also use the coordinate plane to prove or apply congruence criteria as well. Then we will prove the other shortcut or the other criterion we hadn't mentioned back in 11-3, the angle side criterion, and develop the HL criterion, which we'll learn what the HL stands for and where that comes into play. But if you would, go ahead and draw a line right above number 2. And just recall, when we draw a line, it means we're going to pause the video, try to complete the work on our own before completing up into that line. So pause the video, do what you can before playing through. So hopefully you took some time. On A, they ask you to use the distance formula to find each length. So this is a great review of the distance formula. You'll notice that all my work is kind of scattered about. But let's take a look. So they want us to first find the length of B to D, or line segment BD. So B is located at -2, 1. D is located at -5, -2. So here is the distance formula up here. So we subtract our x's and square them, and then subtract our y's, then square them, then add the two squared values together. And so if you look over here at BD, we found that -5 take away -2 is really -5 plus 2, which is -3. -2 take away 1 is -3. So we have -3 squared plus -3 squared. We do the exponents next. So -3 squared is +9. And so 9 plus 9, we get the square root of 18. You'll notice that I went ahead and wrote BD here again. What we're going to do is we're going to take the square root of 18 and simplify it. The way we're going to do that is we're going to write or find the largest perfect square factor of 18. 18 is what we call a non-perfect square. And so we are going to find the largest perfect square factor of 18. So factors of 18 are 1 and 18, of course, and 2 and 9, and 3 and 6. So the largest perfect square factor of 18 is 9. So we're going to rewrite square root of 18 as the square root of 9 times the square root of 2, because 9 times 2 is in fact 18. So we'll get the square root of 9 times the square root of 2. Now, since we rewrote it this way, and hopefully you can see 9 times 2 is in fact 18, so this math is true here. Square root of 9, 9 is a perfect square. That's the whole point. So when we can actually take the square root of 9, and we get that the length of BD is 3 times, now 2 is not a perfect square, so we will leave it inside that square root symbol, or radical is what it's called. So we will simplify the square root of 18, because it's a non-perfect square, we'll simplify it to 3 times the square root of 2. So the length from B to D is 3 times the square root of 2. Really, that's just a simplified version of the square root of 18. Now, if you're wondering where I got DE, you'll notice that there's no work for DE. We only need to use the distance formula for segments that are at what we could call a diagonal. Notice how DB is on the coordinate plane, what we could call a diagonal. If you have perfectly horizontal or perfectly vertical lines, you don't need to use the distance formula to find the distance between those 2 points. You can simply count the distance. So D is located at -5, -2. E is located at 0, -2. So from -5 to 0, that's 5 units. Same thing with FE. We said the same thing here. 5 to 0 on the x-axis is 5 units. Now, if you notice the work for BE over here, square root of 13, if you're wondering why we didn't simplify it like we did with 18, well, 13 is it's a prime number. Its only factors are 1 and 13. So, and it being also a non-perfect square, square root of 13 is as simple as we can go with it. So notice the length of BE is square root of 13, and so is the length of CE. We left this one last little blank here, CF, because we saw the same thing as BD. So we'll just simplify square root of 18 again, and hopefully it'll sink in. So rewrite square root of 18 as the square root of 9 times the square root of 2. And square root of 9 is a perfect square of 3. Square root of 2 is not a perfect square. So the simplified answer to square root of 18 is 3 times the square root of 2. So if you missed it, Greg's boss asked him if he can prove that these two triangles are congruent. So why would we spend the time finding the distances of all 6 sides of these two triangles? Well, we learned back in lesson 11-2 and really saw it in 11-3 that if 3 sides of one triangle are congruent to corresponding sides in another triangle, the 2 triangles are congruent. So what do we see here in item A? We see that BD is congruent to CF, and we see that DE is congruent to FE, and we see that BE is congruent to CE. So B then says, can Greg use this information to prove that these 2 triangles are congruent? Yes. Using the side congruence criterion. Because 3 sides in one triangle are congruent to corresponding sides in another triangle. And that is enough to prove that these 2 triangles, triangle DBE and triangle FCE, are in fact congruent. So we can use the distance formula. We can actually find the length of these sides to show and prove that the 2 triangles are congruent. As stated previously, number 2, in item 5 of lesson 11-2, we discovered that side, angle, side, and angle, side, angle are not the only criteria for proving 2 triangles congruent. You also discovered that there is an angle, side congruence criterion, and they ask us, what does this congruence criterion state? And then mark the triangles below to illustrate the statement. So pause the video, go back and look at your lesson 11-2 notes, which were from the Desmos activity. Or look at lesson 11-3. I believe I gave you the definition of that criterion there. If you need to, then play through the video to see how you did. Okay, so written in an if-then statement, the angle, side congruence criterion. Now, if you're not catching on to this, the reason they ordered these letters in a specific arrangement is because we're talking about 2 angles and a side. We call it not included, a side that's not between the 2 angles. So if you're not picking up on the order of these statements. So go back to the ones we saw in 11-3. We're talking about two angles here, and because the S is written between the two angles, we're talking about two angles and the included side. Likewise, for what we said on two sides and the included angle. And the order that they write these criterion is very important. So for the angle side, we're talking about two angles and a non-included side of one triangle are congruent to two corresponding angles and non-included side of another triangle. Then the two triangles are congruent. And then they asked us to mark the diagram or mark the triangles below to illustrate the statement. So we're saying something pretty crazy here, and I'm not sure if we're picking up on it. We're saying if this angle right here, and remember, an angle is not determined by the length of the two rays. So we could have an angle with two rays this length, and remember, rays go on forever, and we could say that this angle is congruent to this angle, even though their rays are longer. So consider that. We're saying if we know two angles of one triangle are congruent to two corresponding angles of another. But what's really happening here is this side, this non-included side, whatever length it is, these rays continue to meet the other end of these two sides. So by having this angle and this side, we're kind of locking this angle and this side into place. And even more so, this side, the reason that it's going to hit this angle or this ray at a certain point is because of this angle that it's on. So all three of these parts working together is what makes angle side a viable or valid congruence criterion. So now that we've kind of looked at multiple ways to prove two triangles congruent, we looked at in lesson 11-3, we looked at performing a series of rigid motions that can map one onto another to show two triangles congruent. Now we're actually, in this lesson, we just looked at using the distance formula on the coordinate plane to show two triangles congruent using the side-side-side angles, side-side-side congruence criteria. Now we're actually going to prove the angle side congruence criterion using an actual proof. So let's take a look. Number 3 says the proof of the angle congruence criterion follows from the other congruence criteria. So we're going to use the other congruence criteria to help us prove that angle side congruence criterion is actually valid. So we're going to complete the statements in the proof of the angle side congruence criterion below with our given information and what we're trying to prove. And notice we're trying to prove two triangles congruent. So if you would, go and draw a line below this proof. And as always, try to work the proof up to the line and then play through the video to see how you did. So it could be a rather daunting proof, but hopefully you tackled it on your own. But anyway, we were given that we have two triangles, triangle MNO and triangle PQR. And notice what they're doing here. They're telling us essentially this criteria, that we have two angles, or two pairs of angles, angle N congruent to angle Q, and angle O congruent to angle R, and a non-included side, MO, congruent to PR. So we have these two triangles that fit the bill of this congruence criterion, but we're going to use another congruence criterion to then prove that this congruence criterion, angle side, is valid. So if that's what you were wondering here, that's what's going on. So always mark your diagram with given info. So we're about to prove that this criterion, angle side, is valid by proving the two triangles congruent. So number 1, how do we know that they are two triangles? Well, it was given. And number 2, this is a new theorem. It's actually going to be introduced later in lesson 13.1. But something I believe in middle school was taught, that the three measures of interior angles of a triangle actually equal 180 degrees. It's called the Triangle Sum Theorem. The sum of the measures of the angles of a triangle is 180. And we'll actually explore that. It's very, very interesting how no matter what size triangle it is, for example, angle MNO, when I combine the measure of angle N plus the measure of angle M plus the measure of angle O, I will always get 180 degrees because it's the Triangle Sum Theorem. So we have these three angles that add to equal 180 degrees from triangle MNO, and then we have these three angles that add to equal 180 degrees from this triangle PQR. And so why did we claim or even bring to attention that all three of those angles from each triangle add to equal 180 degrees? Well, if two things, in this case a lot of things, if these three angles, MNO, add to equal 180 degrees, and these three angles also add to equal 180 degrees, they both equal the same thing. So we actually, on step 3, notice this error here, that we can actually say that they're equal to each other. That's the transitive property. When two things, or in this case, these three angles, are equal to the same thing, 180 degrees, they're equal to each other. Well, you notice that I have a couple more arrows here kind of showing how these other statements come into play. So let's press on. So we know these three groupings of angles are actually equal to each other. And then in step 4, we bring in another piece of given information that the two pairs of angles, angle N and Q and O and R, are actually congruent to each other. Well, then statement 4 leads to statement 5. How do we know that two angles that are congruent have the same measure? That's what it means to be congruent angles. So we use the definition of congruent angles to show that angles that are congruent have the same measure. Well, if you're forgetting this idea, the reason we have to change from congruency to equality is back here in step 3, we have an equation. We have to convert from congruency to equality when dealing with equations. So now let's look at what happened on item 6. Now that we know that measures of pairs of angles are equal, statement 3, we said that the measure of angle P plus the measure of angle Q plus the measure of angle R. Now, on step 5, we know that measure of angle O is the same as the measure of angle R. So look on step 6 and look at step 3. We replace measure of angle R with the measure of angle O because of this statement right here. Well, if you now notice that there's two angles on both sides of this equation that are the same. So if we use the subtraction property, we can cancel out both of these measures, whatever they are. We can cancel them out, and we're left with the measure of angle M equal to the measure of angle P by the subtraction property of equality. Well, now going the opposite direction, if we know the measure of two angles are equal, then step 7 goes into step 8 and says, well, if two measures are equal, those angles are congruent. And again, we use the definition of congruent angles. It's the opposite. So if I tell you back in step 4 that angles are congruent, you then can tell me their measures are equal. And then step 7, the opposite, if I tell you their measures are equal, then you can tell me that they are congruent. So start asking yourself, why are we converting back and forth? Well, the end goal was to prove two triangles congruent. So yes, now that we know that the two measures of angles are equal, we need to establish that their angles are congruent. And then in step 9, we bring in our last piece of given information. Segment MO is congruent to segment PR. And then statement 8, statement 9, and I think I drew it from statement 3, but it should actually be statement 4. We have 3 pairs of corresponding parts congruent. We have 2 angles and now what's referred to as the included side. Now that we just proved that angle M is congruent to angle P, we now have 2 pairs of angles and the included side, which we proved in lesson 11-3 that angle is a valid congruence criterion. So by proving that angle M is congruent to angle P, and therefore proving these two triangles congruent using angle side angle, we just showed that angle side congruence criterion is also valid. So we can use other postulates, other theorems to prove new ones true. And we've seen that a lot in geometry this year. Now, if you would, let's take a look at number 4. Below are pairs of triangles in which congruent parts are marked. For each pair of triangles, name the angle and side combination that is marked and tell whether the triangles appear to be congruent. So take a second. This is not a trick at all. We're trying to discover something pretty interesting here, though. Take a second, and if you would, complete item 4A through D before playing through the rest of the video. So there's no trick here, but the combination, the angle and side combination we're looking at for all 4 of these pairs of angles is the side-side angle. And be sure to write it this way, because if you write it the other way, you're actually writing a bad word on your paper. So the side-side angle, 2 sides and a non-included angle. Here we have one pair of sides congruent, another pair of sides congruent, and a non-included angle, pair of angles congruent as well. So this is the side-side angle. So we've already proven several other congruence criterion true, and we just showed that angle side is valid. So let's see if side-side angle is valid. Well, if you notice, half of these side-side angle, the triangles do in fact appear to be congruent, and the other half of these, mainly the pairs in B and D, they don't appear to be congruent. So think about why side-side angle works for some of them and doesn't for others. And I love this illustration right here. I think this is an excellent representation of it. This side right here can be the same length, but not necessarily the angle here has to be the same. So we could actually essentially slide this side in like so, where it's still the same length as the original side or as this side, but this angle here doesn't have to be the same angle. And so because side-side angle does not guarantee congruence for all pairs of triangles, then we got to throw it out. We got to throw it out. We're not going to use it if it doesn't work for all pairs of triangles. But you notice for A and B, it does work, or excuse me, A and C, for those pairs, it does work, which leads into question 5. We know that in general, side-side angle does not always, you might be asking yourself, well, if it does sometimes, let's use it. No, in geometry, it's final. If it doesn't work always, we throw it out. So it does not always determine congruence of triangles. However, for 2 of the cases in item 4, the triangles appear to be congruent. What do the congruent pairs of triangles have in common? If you would, pause the video, answer this question very simply before playing through. So hopefully you figured it out. The reason 2 of the cases appear to be congruent is because they're right triangles. And so because mathematicians were like, we don't want to confuse students by saying side-side angle works only for right triangles and none for others, we actually refer to it as something else, which leads into question 6. In a right triangle, we refer to the corresponding side-side angle shown in items 4A and 4C as hypotenuse leg. So we're not going to refer to it as side-side angle. We're going to refer to it as hypotenuse leg. And if you've forgotten key parts of any right triangle, notice I said any right triangle, the longest side, which is always opposite of the right angle, is known as the hypotenuse. Hypotenuse. And the other 2 sides of your right triangle are referred to as legs. So we're suggesting here that the hypotenuse of one triangle, if it's congruent to the hypotenuse of another, and one of the 2 legs is congruent to corresponding legs on the other right triangle, then the 2 right triangles are congruent, and we're referring to it as hypotenuse leg. So our task in item 6 is to write a convincing argument in the space below to prove that hypotenuse leg will ensure that right triangles are congruent. So we're going to create a very interesting argument using the fact that these are right triangles to provide justification that hypotenuse leg is a valid congruence criterion. So take a moment, try it on your own. There's a lot of space here before playing through the video. So yet again, we're trying to prove this new criterion, hypotenuse leg, true by using another congruence criterion that we already know is true. So I have two right triangles here. And notice they've been marked with the hypotenuse, the two corresponding hypotenae, I believe is the plural, the two hypotenae congruent, and these two corresponding legs are congruent. And so we're trying to prove that that information is enough to show that the two triangles are congruent. And I know the drawing looks like they're congruent, but you know, drawings can be deceiving. In fact, this one actually looks a little bit larger just because of how rough my drawing is. So we learned of a theorem way back when in geometry that if this is indeed a right triangle, then the length of this side right here, A, squared, plus the length of this side squared is equal to the length of our hypotenuse squared, which is A squared plus B squared equals C squared, which is the Pythagorean theorem. And that's true for any right triangle. Notice I labeled these three sides D, E, and F. So A squared plus B squared does in fact equal C squared, and D squared plus E squared does in fact equal F squared because of the Pythagorean theorem. Now, if we've already shown in the diagram that these two sides, corresponding sides, are congruent, if C equals F, then C squared also has to equal F squared. And I hope that makes sense. If C is 4, well then F is 4. Well, if C is 4, then that's 4 squared, which is 16, and F is 4. 4 squared is 16 equals 16. I hope that makes sense. So if C equals F, then C squared equals F squared, and therefore we can use substitution to replace, or technically I believe it would be transitive property because they're the same thing. If A squared plus B squared and D squared plus E squared are equal to the same thing, then we can say that they're equal to each other. That's what this statement is. Well, we've also shown in the diagram that the length of A is the same as the length of D. Well, if A is equal to D, then so is A squared equal to D squared, just like we said back here. So we replaced on this other side of the equal sign, we replace D squared with A squared. And so we now have the equation A squared plus B squared is equal to A squared plus E squared. And notice we have A squared on both sides of the equation. So no matter what A is, we can subtract that value from both sides of the equation, and we're left with knowing that B squared is equal to E squared. Well, if we know B squared is equal to E squared, then B has to equal E, right? Go in the opposite direction. If C equals F, then C squared equals F squared, and the exact opposite is true. If B squared is equal to E squared, then B has to equal to E, which means, and I'll go ahead and mark it now, which means these two triangles, we can show that these two triangles are congruent either by side, 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 or because we have three pairs of corresponding congruent sides, or side angle side, because we know all right angles are congruent. They're 90 degrees, so all right angles. So we could say these two sides, these two pairs of corresponding sides, and this included angle, or because we have all three pairs of sides congruent to corresponding sides in the other triangle, that's enough too. So we just proved the hypotenuse leg as a valid congruence criterion using two other possible criteria. So we have just tackled the two learning targets for 11-4. So as always, go back to the beginning of this lesson, reevaluate your understanding. We've just looked at the angle-angle-side congruence criterion and the HL congruence criterion. So add those to the list. So go back, reevaluate your understanding of those learning targets. And as always, don't forget to do the practice. Thanks for watching.